Thanks a lot for inviting me to give a talk in the learning and mining from graph data. So today I'm going to talk a little bit our work on network inference from Cascades. The work has been done for the past 3 years, so you're going to see the work over a large span. When I prepared the talk, I thought it was 1 hour, and then I realized, oh, it's only 40 minutes. But anyway, hopefully I give you a picture of what we have been doing, and then we can have some follow-up discussions afterwards if you have any question. So social network analysis is a major area. I know that the whole workshop and maybe majority of the KDD conference papers about social network. And it has been there for many years, but obviously more recently it becomes much more attractive because we get access to a large amount of data online. And this literally gives us more tools and also empower us to develop machine learning or data mining algorithms to analyze these data. And the particular problem that we're interested is the information diffusion. So basically it studies how the information is propagated throughout the social network. So it has large applications in viral marketing, media analysis, rumor detection, you can name all. Basically, the setting is as follows. We were given a social network, and the edges were indicating whether a friend is a user is a friend of another user, and sometimes we'll be given the information of the strength of the network, and that's why you see some continuous value in there. And then, given the social network, we say if there's one piece of information from particular user A, and then we observe how the time passes by, the information will actually propagate throughout the network. And this is how we basically try to study how the information is propagated throughout the social network. So in many of the literatures that many different type of diffusion model have developed, we have heard about the simple linear threshold model, and then later there's this discrete independent cascade model, and more recently people started to look at this continuous time in independent cascade model. So these are the models have been developed to model how the information propagates throughout the network. So for us that we're interested in a related but different problem, what we are trying to say is that on social network, a lot of time we do not observe the network itself. And most of the time we will be actually observing the cascade. So what do we mean by this? This is the perfect setting where we have the social network and the strength of the network. And as I mentioned, that there's no observed social network sometimes. The only thing that we see is how the information is propagated throughout this network. For example, whether user B will propagate one information to user E, and the way that we observe them is basically observing the diffusion history. And in our terminology, we sometimes will say this is basically a cascade. And the cascade will basically saying that what time which particular user has adopted a particular purchase or have write something on Twitter. And then we observe this timestamp and also the events. After that, we will collect a large number of these type of diffusion history, and in the end, we will be able, or at least that we're trying to infer what will be this hidden unobserved social network and their strengths. So this is the problem also known as the network inference. As I mentioned, it's basically infer a diffusion network from observed cascades. There's a lot of related work here, just to list a few published in KDD community and also in www or social network analysis community. So what we have been trying to do is trying to say what are the challenges when we try to infer the diffusion network. So one of the challenges that we identify, which seems quite practical in real application, is that sometimes we do not fully observe the diffusion history. Let's say that this is the time that timestamp an event happens, right? A user tweets something or makes some purchases. Sometimes we only observe partial of them, or some of the data or the cascades are only partially observed. And this is what we quantify this as the network inference from incomplete cascades. That is one challenge. The other challenge is sometimes that we may have the following scenario. Most of the social media website is not only this particular activity, whether a user click on something, but also involves that they will post the contents in terms of the news tweets or the Facebook update, right, in terms of their news feeds. So that means that we're trying to analyze information from both the event activity, that is the cascade, but also the content information. And therefore, we call this particular challenge is the network inference from content information. And the last one is also driven from the practical application. In many of the scenarios, what we have been working on is, or noticed is that a lot of these influence networks are actually topic dependent. What does that mean? That means that for some of the topic, let's say on music, there's some particular music dependent or music related diffusion network. And then for sports, there will be also sports related diffusion network. In some of the cases that we only observe the partial information or a limited number of observations for some of the topic that we're interested, well, there's a large amount of tweets, for example, on healthcare or on the presidential election, but there is limited amount of tweets on education, right, or how we can actually improve the air quality in urban cities. So from that perspective, we're also facing the challenge we quantified as network inference with limited cascades. As I mentioned in the past few years, we're trying to address these three challenges. And here I just, using the specific limited about 20 minutes, I want to show you what we have achieved in the past few years. So to make the theme a little bit more organized, I'm going to start with network inference from the content information. This was the paper we published in ICML 2015. So the basic idea, as I mentioned, we try to incorporate content information together with the network inference. So just more specifically, that we say there is this activation-based cascades, there's also text-based cascades. Activation cascades, as I mentioned, that means that we observe at what time a particular event happens. So this is nice, and this is most of the research we have been focusing on. And then on social media, for example, here we use event registry as an example where we're going to see each particular news media when they publish a news and also what is the content of this news. And then we would like to actually leverage information from both the temporal information and also from the content information. So why we're trying to do this? Because we think that incorporated content information will help us develop a better diffusion model. And of course, when we have the diffusion model, it hopefully can also help us to capture better the topics of these documents. And this is where we come from, that we try to incorporate both the content and also the cascade and temporal information. So, so in this particular work, we propose a so-called Hawks topic model. As I mentioned, this is basically a joint model of simultaneously trying to do network inference and topic models from these text-based cascades. So in order to explain the model, which is relatively complex, I first want to give you an intuition in terms of how we try to develop the Hawks topic model and incorporate both the cascade information and content information. So let's say usually what we're trying to, usually what we observe in terms of event-based cascade is that we observe a series of events like this. And then what we're doing is that we're trying to model the cascades through this mutually exciting nature. And this is usually can be modeled through this Hawks process model. And this mutually exciting nature, the advantage of this type of nature is that we will be able to actually monitor and also capture how a posting event will be able to trigger another posting event. So this is one part. And the other part we want to capture in this particular model is that we want to model the content cascades. So which means that we think the content of a document will be similar to the document that triggers its publication. So that means that now we will be able to connect the content information together with the cascade information. And that is essentially how we want to actually model these two types of processes together in one unified model. And next, I'm going to talk a little bit about the specific of the model. Our model, as the name suggested, we base this on based on the multivariate-Hawkes process model. The multivariate-Hawkes process model basically have this can effectively capture this mutually exciting nature, and you can also think of them as aggregated multiple point Poisson process model. And then in this particular multivariate-Hawkes process model, there is a specific parameter which is called the intensity process, which is lambda Vt. That means that it will be associated with a particular node V and also a particular time t. And then you can think of them as the intensity of how much a tweet, the tweets will be posted on social media. For example, when you have lambda Vt multiplied by delta t, that means that you can think of this as approximate the number of posts over the short time of delta t. So, so we call this as the rate, that is the lambda t, and then we think of them can actually be modeled by two parts. One is the base intensity. So base intensity can be captured by mu t, that is the intensity specific to node V. Mu v is specific to node V. And then there's the second part also will be the influence from the previous events, which is shown in here. And usually for the multivariate-Hawkes process model, it will have the following form. That is, we look at all the events happening before the time t, which is sum over here, and then we look at f delta t minus te. So basically, that is, we look at all the previous events, and then we see how they accumulated and have an effect to the current timestamp. So here, f delta t is basically the probability density function of the decay distribution. Sometimes we can use exponential distribution, and sometimes you can actually use non-parametric model to capture that, and learning that from the model. And then on top of that, what we did is that we are also adding this A, UW. So basically, this will actually indicating the influence strength from user U to user V. And if we do the inference, once we learn the parameters, that is the A, UW, then we will be able to learn the strength of the influence between different users. This is basically this multivariate-Hawkes process model. And then after that, what we're trying to do is incorporating the topic information inside this multivariate-Hawkes process model. And the way that we do this, as I mentioned, is that we're trying to looking at from this aggregated Poisson process model. So that means that we will be able to automatically generate their posting time of the events in the breadth first order. The way it works, let's say that we publish all these different type of tweets between two users, and then we naturally will generate this aggregated event. So basically, we are saying that there may be three levels of events happening. First, we have the level 0 events. This basically will be self-triggered events. So let's say user 1 posted an event, a tweet, and then user 2 posted another tweet. And then there's also level 1 type of events. That means that the event will be triggered from the self-triggered events. So for example, we posted another tweet based on the previous content that user 2 posted. And similarly, we have all these tweets triggered by the post by user 1. So after this, then we can follow this. Let's say we have level 2 events, which is triggered by the level 1 events and stuff like that. So if we look at from this perspective, then we will be able to explicitly model the parent relationship between different events. And then after that, what we're trying to say is as follows. That is, we are going to generate the topics for each document as the following. If this is a self-trigger event, then we think the document topic ratio will be generated from a Gaussian distribution associated with individual user. And for those events from level 1, we said that the topic mixing of that particular document on level 1 will be generated from a Gaussian distribution, but its mean is actually determined by the level 0 events, that is the level 0 documents that is triggering this level 1 documents. And then we can move forward with this. So basically, this is the basic model. We won't have the time to talk more details. If you're interested, you can look at the paper. The one thing we would like to focus a little bit is that when we try to join inference, where we try to analyze what is approximating generation process of the parent relationship, that is whether an event is triggered by another event. And this parameter gamma E in here is actually can be approximated by is proportional by with a product of 3 different factors. One is what we here showing here, which is actually a normal distribution, where, as I mentioned, that its topic mixing will be determined by the topic mixing from the previous event. That is, the event triggered this particular event. In there, we are going to measure the similarity between the document topics. And the second one is that we capture the influence between users, and that is the A parameter that we are trying to learn from. And the last one, as I mentioned, will be the decay function, which will be used to model the proximity of events in time. So hopefully, using this particular variational learning formula, you can see a little bit how our model will be able to incorporate both the topic modeling, which is showing here, together with the Hawk's process model, which is shown in these formulas. So next, I'm just going to quickly show some experiment results to see what we can do with this model. So we perform our experiments on 2 types of data set. One is the event registry, which is actually we collect news on Ebola in about 4 months, and we got about 9,000 articles, which generated from 330 news media's website. And then we use, whenever we try to say, how do we know what is the ground truth for influence network? There's no way that we know the ground truth. We use an approximate ground truth. That is, sometimes one news media will copy the information from another news media website, and we use this as one way to validate. It's not perfect, but at least one way to validate this. And then for the second data set, we use the archive data set, which is we got all the papers on high energy physics in 12 years. And then we're going to look at the top 50, 100, and 1,200 and 200 researchers. And in here, again, we don't have the ground truth for the influence network. We are using the citation network as one way, or the pseudo ground truth, to evaluate how well our model is. And this is also trying to list off all the baselines that we compare with. HTM, that is Hawk's topic model, is ours, which will be able to do both topic model and network inference. We also compare with the LDA model or the correlated topic model, which use only for topic models, Hawk's process model for network inference only. And also we compare with this 2-stage process. That is, we first infer the topics, and then based on the topics, then we're going to infer the corresponding influence network structures. So these are the 2 baselines that we're comparing with, which are the 2-stage process. So first, I'm going to show you the network inference accuracy. First on the archive data set. So here we compare the top 50, top 100, and top 200. And here we show the AUC number. So as you can see that comparing with all the other approaches which use only the cascade information or doing this two-step process of doing both topic model and network inference, our model will be able to get about 40% improvement in terms of the network inference. And then for topic modeling accuracy, we evaluate them based on the perplexity. So, and then we compare with the LDA model or correlated topic model. We were able to get also much better results in terms of the topic models. And next, I just want to quickly show you some of the network that we inferred from this archive data set. So these are the authors from on high energy theoretical physics. We are not very familiar with them, but based on the influence network structure we think that there are basically three types of authors. One is are those authors like we show clustered in here. These are the authors who don't publish a lot, but they have their papers actually have very fundamental influence inside this particular community. We also noticed that there are these two other type of authors who are actually publish a lot and also cite a lot. And these are mostly the authors who actually propagate the research outcomes throughout the community. And obviously, the rest are the authors, the majority, like many of us, we are mostly absorbing the knowledge or the information or the research outcome and do not publish as much or do not publish influential papers as much. So this is trying to understand the influence network structure, whether it makes sense or not. And last, we just want to show, we pick up two authors. We look at their topic models to see whether we were able to capture nicely about their research topic. So the first one is Andre Lindy, and this is the buzzwords that we capture through LDA, CTM versus HTM, and that is our model. And then when we look at his website, we saw that our model was able to capture some of the unique words that he published or he pushed specifically on his website. Let's say he focused on the inflation and also the inflationary multiverse theory research. And similarly for the other author, that is Arkady testing, and we were also able to capture the string theory and also the string theory, basically the buzzwords from his research work. And this was not able to be captured by the existing topic model. So we may be asking why. And we think that one of the major reasons is that we look at how his paper was propagated throughout the network. We realize that most of the people cite his work because of his contribution on string theory. Well, there are a lot of other buzzwords in the documents that in the papers he published, but the string theory seems to be the major one that is influential in the community. Okay, so with that, hopefully you get a little bit idea of how we will be able to develop this particular Hawk's topic model, which can model both the content information and also the cascade to infer the influence network structures. So next, I'm going to talk a little bit about the topic on network inference from incomplete cascades. So this was the paper we published last year in NIPS, but we also want to share with you our KDD reject experience. So as you know that we're always interested in publishing in the top venue, and KDD is one of them. So at that time, we identified this interesting problem. That means that we are interested in identifying what is the property, what will happen if we have some partial information that is missing, that means that we will not be able to observe them. And then at the beginning, we do this most empirically. We do a lot of experiments and provide the analysis on these network inference model to say, that based on the observations that we collected from the synthetic data set and also the observation data set, by withholding some of the information that is artificially generating the missing observations, we see how different algorithm will perform. We were not able to give any theoretical results because the complexity of the network inference models. For example, when we try to look at the model of the Hawkes process model, it's really difficult for us to produce any theoretical results. So I have the student Xinran, who has already graduated, and at that time he was really trying hard to graduate. And I told him that you have to publish a paper, and he tried really, really hard until he found, there may be alternative way, or maybe we can answer a different problem. And that is essentially where we get started on this particular paper. So he realized that what can be done is that we can analyze the behavior of influence functions in presence of missing data rather than looking at the inference model itself. So therefore, in this paper, we're mostly focusing on looking at the behavior of influence functions instead of the network inference problem itself. So for those of you who are not familiar, I just want to give you a quick introduction of what is the influence function. So basically, the influence function is generating a mapping from the seed sets to the vectors of the marginal activation probability. So basically, let's say that you were given the seed set, that is, here is just one node, A has been activated. Okay, and then let's say that we try to, given this diffusion network structure and their strengths, which we do not know, what we are only observing is basically what type of activation, what type of nodes have been activated. And then based on this diffusion model, we will, based on this diffusion observation, then we will be able to learn this marginal activation probability. So that means that what is the probability of node A will be activated given the seed and etc. So we're trying to learn this marginal distributions. There are two ways to look at it. One way is, as I mentioned, this will be the marginal distribution associated with each node. That is, what is the probability this particular node will get activated given the seed nodes. Another way to look at this is to say that, we are going to look at the total influence function. That is basically sum over all the nodes of their marginal distributions. So in this paper, we look at marginal probability, but another way to look at it is the total influence function as well. So also, we want to say that in this one, we're mostly focusing on the activation-only cascade. That means that we do not observe at what time the node will be activated. What we only observe is that at the end, whether a node will be activated or not, or that by time t, whether the node will be activated or not. So this is basically the specific case that we're focusing on. That is the activation-only cascades. So the setting now will becomes as follows. That is, given a seed node, given the cascades that we observe, only the cascade without the temporal information, we want to learn this influence function. That is, whether a particular node, what is the probability a particular node will be activated given the seed sets. Okay, so this is our objective. And then next, we need to set up this a little bit. We want to evaluate the accuracy of the learned influence functions. So there are many ways that we can do this. One way we can do this is basically we try to evaluate this based on the L2 loss. So here we'll list it basically that we're comparing the probability with the true model, and then we evaluate them based on the L2 norm. There are many ways that you can evaluate. So in this paper, we're using the L2 loss, but obviously this is mostly due to the analytical convenience. After we get this, then we're going to get expectation. Here, the expectation, the error of the influence function that we learned will be the expectation of this L2 loss. And then the expectation will over the seed sets. This will be generated based on some probabilities, or sample based on some probabilities given the whole sets. And the other one is the activation sets. So that means that we're looking at all the different type of activations, the observations of the activation, and this will trying to take the factors in terms of what seed we're using or what type of activation we observe. We're just looking at the expectation, that is average behavior of this learned diffusion function. And then we also define the so-called pack learnability of the influence function. I don't want to go into the details, but basically you can think of them as follows. That is, we're looking at if, let's say, we learned this diffusion function f, and also here f star is the optimal one. If the probability of the error of the true one and the probability of the difference between the error of the true one versus the error of the learned diffusion function is larger or equal to epsilon, is smaller than some particular value, then we say, oh, this is pack learnable. Okay, this is the definition of where we get started. As I mentioned, there's no time for me to go through all the details, but here I just summarize what is the known results, and then I will summarize our discoveries. So for the known results, basically for the linear threshold model or independent cascade model, there has already been known some pack learnable algorithm, and with this falling sample complexity. And also for vector model, people also were able to get some nice results. But these are all the analysis for complete observations. What we're trying to do is that we're extending their analysis for cases where we have missing data. Yeah, this is what I mentioned already. Basically, that you have the seed and you have the activation. This is what you're observing. And then we said this will be missing activation. That means some of these activations will we will not be able to observe them. And then we try to infer this. So one of the particular parameter that we're trying to capture is so-called the missing rate. Here we call them as the retention rate. That is the probability that this particular activation will be retained in the observation or not. So here we use the value R as the retention probability. And then after that, we have the following, that we will assume the data will be missing at random. It's not literally practical in many of the real applications, but for analysis purposes, we assume the data will be missing at random with probability 1 minus R. Okay, and next I'm going to show you the main results. So what we have developed is as follows. That is for the incomplete cascades, then we will be also able to derive this pack learnable algorithm, where we will pretty much retain the same sample complexity as before, except now we're adding additional term, which is 1 over gamma to the power of 8. So you may be questioning where this comes from. This is basically coming from that if some data are missing, then we will actually need significant larger number of observations in the end to get similar performance as what we have if the data or observations are complete. And the algorithm that we develop are rather complex, and later we also develop this improper pack learning algorithm, which dissatisfies this property instead of the stronger property, but the algorithm is much more efficient. So if you're interested, we can talk offline, or you can look at the paper that we publish in NIPS. Here is really trying to give you a quick picture of what type of theoretical analysis results we can get. To summarize, basically that means that if the data are missing at random, then we will still be able to develop this algorithm to effectively infer the influence functions. However, the number of observations, that is the number of cascades that we observe, will be much more than before. So after that, I'm going to also quickly tell you what we have done for network inference with limited amount of cascades. The way that we do this is quickly trying to summarize is that we're trying to learning these network structures from lots of other network structures. And we assume that all these network structures will be generated from a prior graph. And that is where the whole thing will be able to unfold. So this is the paper we published in Wisdom this year. But basically, as I mentioned, that for some of the topics that we have large number of cascades, for other for other topics, we do not have as many cascades that we can observe to effectively infer the network structure. And then what we're trying to do is that why don't we actually joint infer the diffusion networks or the influence network structures at the same time so that we can leverage information from these popular topics and which will be able to infer effectively both the diffusion network with popular topics and less popular topics. So that's the basic idea. And the way that we're doing this is saying that all these networks will be generated from a common prior. And this is basically what we're trying to do. That is, we will be able to jointly infer these multiple networks by assuming the networks coming from the same prior distribution. And we call this model as the multi-cascade model. So basically that we have this particular prior for all the networks that we're trying to learn. And then these priors that may be actually generated either from the latent space model or from the stochastic block model. So once we got this, the end of the day is that we're trying to do the following. That is, we try to infer what it will be the prior parameters associated with the prior of the graph. And then we are also trying to effectively infer each individual graph associated with a specific topic. So the way that we do this is basically trying to do maximum likelihood estimation. Similar as before, we say, okay, we're trying to learn the probability of each individual graph given the parameters of the graph prior will be a multiply of two things, right? So this first, we're going to generate the graph. We're going to generate the graph based on either the latent space model or from the stochastic block model. And then after we get the graph, and then based on the graph, we're going to generate the cascades. And later, we're going to do the maximum likelihood estimation. We're trying to learn the parameters theta, that is the parameters associated with the graph prior, and also we'll be able to learn the graph itself. I'm not going to go through the details, but basically we use EM algorithm, and then some steps that involves proving that the objective function will be submodular so that we can significantly reduce the computational complexity of learning the graph. So we did this for the Twitter data set where we were able to get the tweets on 5 different categories: Iranian, Haiti, earthquake, technology, climate, and US politics. And then we will be able to jointly infer the diffusion networks for each individual topic. And then we compare them with the baseline, which means that we're learning each individual diffusion network separately, or we're just aggregating all the information together so that we can enough amount of data to learn this common diffusion network, which is not accurate, but at least better than nothing. So basically, using our method, we're able to get better results in terms of the network inference accuracy. And some of the networks that we learn seems to be more informative than the others. So just summarize what we have in here. We basically propose this multi-cascade model, which will be able to jointly infer the diffusion networks. And this is achieved by actually assuming that all the graphs will be generated from a common prior, and we're going to learn the prior parameters from the data automatically. So this is basically what we try to do. And for future work, we say that we try to also infer the influence strength rather than the network structure itself, and also trying to decide what will be the graph generation prior. Right now, we have tried stochastic block model and latent space model, and there may be many other different type of graph priors that we can adopt. So to just summarize, basically in this short 40 minutes, I just give you a quick glimpse of our research work on inferring the diffusion or the influence network structures from cascade observations. We think it's really challenging task, especially when we talk about the robustness in terms of the missing data, the limited observations. There's still a lot of research work that we can do. For future work, we look at basically two different directions. One is that we infer all these different type of diffusion these influence networks, how we can validate whether they are correct or not. Right now, we are mostly using either the synthetic data set or some auxiliary or approximate ground truth. The question is that how we will be able to actually do experimental design so that we can effectively validate all the hypotheses that we have generated using the machine learning model. And the second one is that we always are interested in influence maximization, and we always assume that, oh, you were given the graph and also their strengths. But in practice, what will happen is that we do not have this particular graph or their strengths. Or now we will be able to infer them, but they're actually noisy. So the question will be how we can actually achieve this maximum influence from the noisy infer network that we learned from the data. So with that, I would just like to thank the funding agency and also the PhD student, Xinran, who is the major author working on all these papers, and also our collaborator, David Campi and Liz Gitter. Thank you.